Imagine yourself seated by a window on a clear night, tilting your head back to gaze upon a sky brimming with twinkling stars. The light from those distant luminaries seems to whisper ancient secrets of the cosmos. Have you ever pondered whether the universe is truly infinite as we might assume, or if it conceals some chilling truth beneath a clever illusion? This is the very nightmare that confronted two of humanity's greatest minds, Isaac Newton and Albert Einstein, a torment that has echoed through centuries and continues to haunt scientists today. Newton, the revolutionary figure who transformed physics with his law of universal gravitation, realized with horror that if the universe were infinite and static, the gravitational pull among countless stars would collapse everything into a vast, chaotic mass, much like an avalanche swallowing all in its path. Unable to explain this, he resorted to invoking divine intervention, feeling as a pure scientist the impotence and awe before the mysteries of creation. 300 years later, Einstein overturned Newton's flat stage with his general theory of relativity, depicting the universe as a flexible fabric where gravity is not an invisible tugging force but the curvature of space and time. Yet he too plunged into a similar abyss. His equations revealed the possibility of a closed universe, finite yet boundless, akin to the surface of an immense sphere where one might walk eternally without finding an edge. For Einstein, who yearned for a harmonious and infinite cosmos, this evoked the suffocation of being trapped in a windowless room, stirring a sense of everything repeating infinitely beneath an illusory shell. To grasp these concepts more fully, let us embark together on a simple yet potent thought experiment often employed by scientists to probe secrets beyond human perception. Picture yourself as a daring astronaut aboard a transcendent spacecraft capable of surpassing the speed of light, hurtling straight ahead in one direction without ever turning back. Time passes not in mere days but in millions of years. Stars streak by as faint trails of light, and the hum of your ship's engines resonates like the steady heartbeat of the universe itself. Suddenly, a familiar blue planet looms before you. Excitement surges at the thought of discovering a new world, but as you draw nearer, you recognize it as Earth, your point of origin. You have returned without altering course. This mirrors traversing the spherical surface of Earth, where endless walking brings you back to the start without encountering cliffs or boundaries. It embodies the notion of finite infinity in 2 dimensions, challenging our intuition while evoking wonder and a touch of dread. Our own universe, in its familiar 3 dimensions, might operate similarly but at a far more intricate level, like a multidimensional sphere we cannot fully behold. This idea is far from novel. Indeed, 2,400 years ago, the ancient Greek philosopher Aristotle gazed at the night sky and harbored similar musings. He questioned how an infinite universe could rotate harmoniously and championed a spherical model that dominated human thought for 2 millennia, imagining us enclosed in a vast box with clear boundaries. Then Newton arrived, kicking away that box with precise calculations of gravity, recasting the universe as an eternally unfolding infinite stage. Yet as he delved deeper into his computations, he uncovered flaws. In an infinite, static cosmos, the gravitational forces of innumerable stars would gather all matter into a colossal muddy clump, with nothing to prevent it. Newton felt terror before this logical paradox, sensing the universe mocking him. He could only appeal to a divine sensorium to account for its eerie stability. Today, we know the universe is neither static nor unchanging but expanding. This revelation stems from Edwin Hubble's discoveries in the 1920s, where he observed galaxies receding from one another at astonishing speeds, much like dots on an inflating balloon drifting apart. Reliable sources, such as recent reports on the James Webb Space Telescope, have updated this understanding, confirming the universe's expansion rate at approximately 70 km per second per megaparsec. This value, known as the Hubble constant, has been measured in 2025 by instruments like the James Webb Space Telescope and the Dark Energy Spectroscopic Instrument, DESI, to range between 70 and 76 km per second per megaparsec. However, a persistent controversy dubbed the Hubble tension endures, arising from discrepancies between values derived from the cosmic microwave background radiation, around 67, and local observations, around 73 to 74. This mismatch demands a re-evaluation of the universe's components, perhaps hinting at undiscovered physics. Scientists worldwide, including those in Korea, emphasize that the universe is not merely finite but dynamically evolving every moment, with ongoing data from the Atacama Cosmology Telescope in 2025 reinforcing this tension and suggesting pathways to resolve it through refined cosmic maps. Einstein propelled us further in 1915 with his general theory of relativity, replacing Newton's flat stage with a pliable mattress where gravity manifests as the warping of space-time. Envision lying on a soft mattress when a heavy bowling ball rolls nearby, creating a dip. This is how planets curve the surrounding fabric, causing other bodies to fall into orbits. But this raises the ultimate question: could space curve so excessively that it loops back into a closed ring? To discern this, we must distinguish two key concepts: curvature and topology. Consider a ripe orange under sunlight. Its peel gently bends to the touch, representing local curvature, the view from close range. From afar, however, it forms a complete sphere, a closed shape. This is global topology, the broader perspective. Similarly, an ant crawling on a Möbius strip, that peculiar twisted loop with only one side, might perceive its world as flat and infinite. It could wander forever without realizing the repeating cycle, unaware even of its body inverting. We might be that ant, adrift in the universe, oblivious to being ensnared in a multidimensional curved structure. Einstein highlighted curvature in space but left open whether it connects into a closed loop. To test this, we cannot step outside the universe to view it wholly, but mathematicians provide tools like the Friedmann-Lemaitre-Robertson-Walker equations, abbreviated as FLRW, which incorporate the average density parameter omega. Omega is no mere physical number, it decrees the geometric fate of the cosmos. Let us conduct another experiment: draw an enormous triangle among the stars. If omega equals precisely 1, the universe is flat like a Euclidean tabletop, with the triangle's interior angles summing exactly to 180 degrees, and you could fly forever without return. If omega is less than 1, matter is too sparse, yielding a saddle-shaped hyperbolic space where angles sum to less than 180 degrees, leading to eternal expansion and a frozen end. But if omega exceeds 1 even slightly, abundant matter curves space spherically, angles sum over 180 degrees, and the universe is closed and finite. Data from the Wilkinson Microwave Anisotropy Probe satellite in 2001 and the Planck satellite in 2013, as reported in 2025 by Korean media and international scientific journals, place omega at approximately 1, with the Planck 2018 measurement of total omega at 1.000 plus or minus 0.002, indicating near flatness but hinting at slight positive curvature. However, scientists like Katie Mack from North Carolina State University warn in her 2020 book The End of Everything that such margins might be mere noise, favoring a flat universe. Nonetheless, the closed curvature idea chills many with its implication of living in a finite bubble. Updated measurements from the South Pole Telescope in 2025, releasing sensitive cosmic microwave background data, further support this near-flat geometry while allowing room for subtle deviations. And the discovery by French astronomer Jean-Pierre Luminet, correctly named, not misconstrued as Paul Kearns or Jean-Pierre Luminet, shook the scientific community. In 2003, analyzing Wilkinson Microwave Anisotropy Probe's cosmic microwave background radiation, he noted a deficit in long wavelengths, no large temperature fluctuations beyond 60 degrees, akin to a small bathroom failing to contain deep bass notes. This suggests the universe is smaller than our observable horizon, leading to the Poincare dodecahedral space model, a form like a soccer ball with 12 pentagonal faces, but multiply connected. Traversing one face transports you to the opposite with a 36-degree rotation. It is finite yet boundless, with volume 80% of our visible horizon. Light echoes like in a hall of mirrors, distant galaxies, potentially ancient images of our own. Subsequent Planck data, as per a 2019 Nature article, found no clear symmetric circles, but researchers like Neeyesh Afshordi at the Perimeter Institute infer evidence might lurk in the noise. The forthcoming Lightbird satellite, approved in 2025 to advance following key decision points and slated for launch in 2032, will scrutinize cosmic microwave background polarization to verify this, as discussed on reliable social media like NASA accounts and physicist Brian Greene's feeds. If proven, the universe transforms from cold infinity to a romantic, topologically intricate diamond. Yet if the idea of the universe cycling within a dodecahedral box fills you with despair, brace for a greater shock: time may not exist. How many years have you lived? The answer might be none. In physicists' eyes, time is mere illusion. Draw a deep breath, feel your steady heartbeat, hear the wind brushing the window, and accept that past, present, and future unfold simultaneously. The crying infant in the hospital, the adult reading these words by faint screen light, the elder on a sickbed, all coexist in four-dimensional space. As three-dimensional beings, we are blindfolded from seeing the whole. Everyday evidence? Activate your smartphone's global positioning system. It achieves meter precision by adjusting time between satellites 10,000 kilometers away and Earth. Special relativity proves high-speed slow time, with satellites lagging 7 microseconds daily. General relativity shows weaker gravity accelerates time, adding 45 microseconds. Netting, satellite time runs 38 microseconds faster, uncorrected, positions Earth by 11 kilometers. The 1971 Hayfel-Keating experiment confirmed this with atomic clocks on aeroplanes. Newton viewed time as an absolute river, but Einstein shattered it in 1905. Simultaneity is relative: a near light-speed year-long flight returns you to an Earth aged centuries. This leads to the block universe, a colossal ice block where space is length, width, height, and time an extended dimension. The dinosaurs' extinction, Qin Shi Huang's ascension, you're reading this line now, humanity's demise, all frozen like bubbles. You do not live but exist as a static worm along a time trajectory, experiencing the illusion of now. Quantum mechanics advances further. The 2022 Nobel laureates John Clauser, Alain Aspect, and Anton Zeilinger demonstrated quantum entanglement, where particles thousands of kilometers apart react instantly, challenging causality and temporal order, what Einstein called a spooky action at a distance. The 1967 Wheeler-DeWitt equation merges quantum and general relativity without a time variable. Time emerges like temperature from molecular motion. Carlo Rovelli, in his 2018 book The Order of Time, infers time arises from entropy, while Julian Barber shares on social media that time is illusory and the universe static at deep levels. In 2025's recent advances, quantum gravity research views time as an emergent illusion from quantum entanglement, with studies showing opposite time arrows in quantum systems. New theories integrating gravity with the quantum realm redefine time's essence, including discoveries of dark states where entanglement persists 600 times longer, resisting decoherence and blurring temporal boundaries. Yet do not despair. Quantum mechanics offers hope through Heisenberg's uncertainty principle. The future is not fixed, each quantum collapse branches anew, harboring free will. Time may be a river, an ice block, or a brains program, but you, unique cross-section with heartbeat, screen glow, fears, joys, are real. The universe is stranger than imagined, as Gene Klein might say. What do you think? Is the universe topologically finite or cold infinity? Does time exist, or is it illusion? Gaze at the stars and ponder. Their light may be your gaze from billions of years ago, returning to greet you. Until next